Hello everyone, my name is Henrique, and today I'm going to be presenting a work that was developed in my undergrad course in the State University of Feira de Santana, and supervision of the professor, Dr. Souza, that has the title Spectral Synthesis and Gas Kinematics of the Peculiar Gas, ESO 293 EG 37. So, the work was divided in these topics and the motivation. The motivation of this work, it was developed in a ESO observatory here in Brazil that hosts the biggest telescope in the Brazilian ground that have a radius of 80 centimeters, like 1.6 meters of mirror, and was worked to merge tidal effects and collision with peculiar galaxies, particularly of the category 15 and 7. The galaxies with jets, tails, debris, and other groups. Our goals here are to obtain data regarding the ionization mechanism of the nebular gas, which complements the classification made in an article that we published in 2021. Determine some physical parameters and identify possible remains of the interaction by means of the rotation curve. And the last objective, kind of subproduct of the work, are used the spectral synthesis to determine the age and metallicity of the components of the axis that we took the spectra of the galaxy. So here is the galaxy. We can not see very well on the slide, but we have here a matter loop, and we have in the red dotted line a slit of the spectrum that we took. We use the method of the long slit spectra, that we use a slit to take an axis of the galaxy, and we cut this slit in some more a lot of little slits, and we have little sections of this big slit, and we see the spectra of each section. Okay, this galaxy is an emission-line galaxy. What means that it has a lot of gas, and this gas is ionized by some way. It could be active galactic nuclei. It could be OB stars, like stars that have a high continuum in the blue and ultraviolet part. And we can classify this galaxy like the type of the galaxy that the spectra present. Like here, where the little hand are favorite one spectrum that have the Balmer transition lines larger and the forbidden transition lines shorter and narrow. And here we have favorite two galaxies that have the all lines narrow and have the forbidden lines very high and the relatively low transition of Balmer, transition of the hydrogen lines lower. And here we have H2 region that have hydrogen lines very high and forbidden lines very low. And here we have low ionization nuclear emission region that have a little low source of energy to ionize this gas, that shows lines that have a little bit less potential to ionize, like neutral oxygen, and sulfur 2 here. The instrumentation used to acquire this data was the telescopic vacuum element, the spectrograph, the detector is the ECON, and the diffraction grid 300 lines per millimeter. To the calibration, we use helium and argon lamp. And to reduce and explore this data, we use the software IRF. That it is a collection of many packages that can help to reduce and analyze astronomical data. To make the spectral synthesis, make a composite spectra of the stars that lies on the galaxy. We use the STARLIGHT code that are developed by the Universidade Federal de Santa Catarina. Here, it is the parameters of the synthesis. We use the stellar libraries Bruce in Charlotte to compose the spectrum. We use the evolutionary model Padova 1994, and the Redlin, Lowndes, Carzetti, and Cardelli. The initial mass function, I have to explain this. It is basically a probability function, kind of probability function that determines how many stars of a determined type that has a little mass or a big mass that will burn on that period of time. So we have to determine these parameters to make the spectral synthesis. Here we have the luminous profile of this galaxy. It should be like a Gaussian, not appear like a Gaussian. We have 2 minutes. Okay. We have two structures, region B and region A, that can show like remains of interaction with the main body of the object. Here we have some physical parameters that we determine of the galaxy. Here we have the rotation curve of the galaxy, that is velocity in function of the radius of the galaxy. Here we have called U-shaped profile that indicates the interaction with another object. Here we have the rotation curve of the region B of the galaxy there, and we have a rotation pattern here, and that means that we have another body rotating along with the main object of the galaxy, or dominated by some kind of tidal effect or merge of the galaxy. Basically, it should be, it might be a merge some million of years ago. Here we have the result of the synthesis. We have the stellar spectra, we have the galaxy spectra, with the nebula spectra that are the galaxy spectra subtracted by the stellar spectra. Then we have only nebula gas lines. Here's some results of the synthesis. We have a blend population of 27% of young stars. We have 72% of intermediate stars. It have this metallicity that are quantity that quantifies elements that are higher than helium on the star populations. So we have this based on the solar metallicity. Here we have the distribution of age along the galaxy axis. We have the little more stars with old age near to the interaction region. That means that the interaction could trigger the birth of new stars, and that's occurred some million years ago, and it produced a lot of old stars and are triggering more stars to produce. Here we have the distribution of the metallicity, and we have a region with high metallicity near to the interaction region that shows that we have a rich area near to the interaction. That, how can I explain? It is subproduct of the interaction. The interaction helped to produce stars, and the stars blow up and enrich the interstellar medium with more elements. Here we have the BPT diagrams that help us to determine the type of the ERG that the galaxy is. We have a galaxy here that are between the H2 galaxy and the AGN branch. We classify in this work like a galaxy intransition of a H2 region to a liner. That means that there is the ionizing medium of the gas are transiting to blue stars to AGN effect in the center of the galaxy. More BPT diagram, a run diagram that do the same thing that the other diagrams are doing. And the star forming height, we can measure the rate of birth of stars based in the emission line of the hydrogen alpha. The measurement was this one, 0.22 solar mass by year. That means that the galaxies are producing a tiny bit of the proportion in stars by year. That don't configure a starburst galaxy. That could configure a H2 galaxy, but are expected to a liner galaxy. Here is the conclusions. We have the evidence of interaction in the region southwest of the spectrum. We have density of old and high metallicity stars in the region southwest that complements the first result. And we have the spectral classification and the low star formation rate of the galaxy that complement the other results. Oh, that's it. And here are the references. Okay, that's it.